Hey everyone, today we're going to take a look at periodic behavior, and then we're going to dive into how we can take the information that we learned from our previous unit in trig geometry and graph sine and cosine as actual periodic functions. So let's get into it. A periodic function is basically going to be a function that repeats itself over regular intervals. So in other words, you're going to have y values that are repeating over a regular interval of x values. Now, if a function is not periodic, typically it's called aperiodic. So with that information, I want you to take a look at these two functions over to the right here. And I want you to decide if both of these are periodic, if one of them is, or if neither of them are. So if you guessed that the first function is the periodic function, you would be correct. The second function is aperiodic. So the reason for this is that you can actually see visibly here that this function has a start and end where I've just highlighted it. And then if we move along to the next section of this function, we can actually see that that pattern is actually exactly the same. It's almost as if we took that yellow highlighted portion and just copied and pasted it over right after that yellow portion ended. Now, this one over here on the right has some sections that are similar. So here, here, and here. However, it's not regularly repeating. In between these, we have different little mountains that are different heights, and therefore this one on the right is not periodic or aperiodic. Okay, so basically you're just looking for a pattern that regularly repeats. As soon as it finishes, the pattern should start again. So most of the time when we talk about the next few things here, so amplitude, cycle, and period, we talk about more like wave functions. So I am going to show you some kind of general periodic functions, but these are more applicable once we get into actual like smooth curved wave functions. So when you see a wave mentioned, we can find the amplitude of just regular periodic function, but it's more applicable with waves. So amplitude. The amplitude of a wave is basically going to measure the displacement from a resting position. So in other words, when you go to calculate amplitude, it's actually going to be half of the displacement from the minimum to maximum point on your graph. So I can easily calculate amplitude by doing max minus min over 2. So let's take a look at that in our example over to the right here. So firstly, we're going to ask the question, is this a periodic function? Okay, if you answered yes to that, you would be correct. We can see kind of like a continually repeating pattern over all of this here. So we'll see that the pattern is repeating, and as soon as it stops, it starts again. So this would be considered periodic, yes. And if so, what is the amplitude? So in order to find the amplitude of this function, we want to locate the highest y value and the lowest y value, the maximum and the minimum. So the highest y value that I can see here is occurring at 3, and the lowest y value that I can see here is occurring at -1. So that means that our maximum is 3 and our minimum is -1. So basically from this middle position right here, if we kind of chopped this graph in half horizontally, I would be looking for the displacement from the middle to the max, and that should actually be equal to the displacement from this middle to the minimum as well. So you can see here that if this is 1 and we go up to 3, that's 2 units. And if the middle is 1 and we go down to -1, that's also 2 units. So I should expect, if I were entering this into the formula that I showed you to the left here, should expect that my amplitude will come out giving me a value of -2. So if we do max minus min over 2, we get 4 over 2, which gives us an amplitude of 2. Just as we expected. Also, amplitude is always positive because it's talking about a displacement from the rest to the maximum or from the rest to the minimum. So this is always like a number of units, it can't be negative. Okay, cycle and period. So the cycle of a periodic function is essentially one complete wavelength of your function. One cycle, if we're kind of looking at thinking about this in terms of like a pattern that's repeating, one cycle is going to be one complete section of your pattern before it starts repeating again. And then we also have period, which relates directly to a cycle of a periodic function. And the period is going to be the horizontal displacement of one full cycle. So it can be measured from any two corresponding points on adjacent waves. For instance, I can measure a period from a max to a max, a min to a min, or any other two corresponding points. So for instance, we could do max to max and measure the number of units between there. We can also do, like I said, min to min, so I can measure the units between here. We could also just choose like any random point on here as long as we can see where it happens in the next cycle. So I'm noticing that this is kind of like the exact same point in both of these cycles, and that can also be used to measure my period. I could also use this point right here. Okay, I would measure from here to here. No matter what I choose, I should end up with the same period. Okay, so let's actually take a look at finding how many cycles are here and also the period. So how many full cycles do we see in this periodic function below? So if we start all the way at the very left side here, I can see one complete section of the pattern there, and then it starts repeating here. So let's just kind of mark this off. So I think I can actually see two complete cycles, and then I see a little bit of one starting, but we see two full cycles shown. And we're going to determine the period and the amplitude. So the period, like we said, we could measure from, let's say, here max to max. And you're basically just counting the number of units. Now, what you could do in order to figure out the period is just take your higher x and subtract your lower x. So here we would be doing like 3 minus negative 5. Or sorry, that would be 1. Just kidding. 1 minus negative 5. Okay, so here's the x value, 1 and negative 5, and that would give me 6 units. Okay, or you can simply just count 1, 2, 3, 4, 5, 6. Period as well as amplitude are always, these are both always positive because we're talking about displacements. Basically just a measure of number of units. So it actually can't be negative for either of those. And then for amplitude, we're looking at the y values. So the maximum here I can see is at 3 and the minimum is at negative 2. So when we calculate amplitude, we're going to do max minus min over 2. Or you can simply count the number of units from minimum to max and just kind of divide that in half. So here we would get 3 minus negative 2 over 2, which gives us 5 over 2 units. Okay, and I think I'm just we'll leave that in exact values there. 5 over 2. Okay, so the cool thing about periodic functions is that we can use periodic functions to predict future values on our function because we know that this pattern is continually repeating. So what we're going to do is we're going to take a point that we can visibly see on our graph, and we can add or subtract multiples of the period to the x value of that point. And each x value that's generated from adding multiples of the period will actually share the same y value of that initial point that I choose. So there's kind of like two ways that we can do this. So part A is going to show us the first way that we can use this. So determine 4 values such that f at x equals 2. So that means we're determining 4 x values where y is equal to 2. So I see a couple of them here. I have one here. This one I don't really want to estimate. So I'm just going to choose the ones that are on exact values. So I can see that f at negative 6 equals 2. I can see that f at 0 equals 2. And I can see that f at 6 also equals 2. Okay, this is the same function that we were looking at previously. So this function does have a period of 6 units. as we found in the previous question. So you'll notice, firstly, that each of these is 6 units apart, and that should make sense because when we say the period is 6, we mean that the pattern repeats every 6 units. So I can imagine if I count forward 12 or 6 more units, I'll be at 12, and that's actually going to give me a y value of 2 as well. So if I take that and I add 6, I will get f at 12, and I know now that f at 12 is also equal to 2. I can add another multiple of 6. Let's say I take 6 and I add 2 times 6, so I add 12. That's going to give me f at 18, or I can just work off of this, of course, as well. That's also going to equal 2, okay? Or I can take this and I can subtract values of 6 from there, and every value that I get is going to have a y value of 2. So if we subtract 6 once, we'll get 12, negative 12. That will also give us a y value of 2. Okay, so no need to continue the graph or anything like that. I know all of these values, they're all 6 units apart. They're all going to have a y value of 2. So that's one way that we can use this. We can also use this kind of like in reverse to predict y values that are not on our graph. So let's take a look at f at 8. So f at 8 obviously is not on our graph here. It goes up to 7. So what I'm going to do here is add or subtract as many values of 6, because the period is 6, to 8 as I need to get back to a point that's on our graph that I can actually visibly see. So if I add 6 to this, I'm going to get f at 14, which is actually not visible on my graph. So I think the best course of action would be to subtract one unit, one multiple of the period, which will be 6, and we'll get f at 2. And that's actually something that I can see on my graph here. I see that f at 2 is actually equal to 1 on the y-axis. So I know f at 8 and f at 2 are equal. They're 6 units apart, which is the period, which means that they have the same y value. Okay, so let's take a look at f at negative 10. So negative 10 is all the way over here on our graph. So I think I'm going to need to add multiples of 6 to get back to a value that I actually know here. So if we add 6 once, remember I can add any multiple of 6. I could add 12, I could add 18, and so on. But if I add 6 once, we're at f at negative 4, and that's actually visible on my graph, so that should be good. That also has a value of 1. Okay, and then f at 14, if I were to take 14 and subtract 2 times 6, or 12, I'm actually getting f at 2. So f at 8 and f at 2 and f at 14 and f at negative 10, they all actually have the same y value of 1. Okay, so you're going to do a little self-test here. I want you to predict f at, hold on, let's see. F at 17. Okay, use your graph and use your knowledge that you just figured out to see if you can predict f at 17. Okay, so if you've had a second to try this out, if you haven't, make sure you pause the video, try it out yourself. But if you've had a chance to try this out, I'm going to subtract, if I only subtract one multiple of 6, I'm going to get f at 11, which still isn't on my graph, so I'm going to subtract 12 here. And we're going to get f at 5. And if I look at my graph, I can actually see that f at 5 equals 0. So f at 17 and f at 5 are equal. And f at 11 as well. Okay, so we're going to do a little investigation. In order to do this investigation, I would suggest kind of printing this out or drawing out a graph like the one below. So what you want to do is set up a table of values for sine and also cosine that goes from 0 to 360 degrees, so one full rotation, up by 30s. And then when you set up your graph here, you're going to set up your angles, kind of like the x-axis here. So you'll see I have like 30, 60, 90, and so on, so going by 30s. And then I've done my y-axis going by 0.25s. So if you need to, you can take a second and kind of copy this out on a sheet of paper and then we'll get going with the investigation. So just pause the video, copy it out, and get ready. Okay, so the first thing that you're going to do here, I'm going to give you a little bit of direction and then you'll kind of finish up the rest of this. But grab your calculator. You want to be in degree mode, and this is the function f at x equals sine x. So we know what to do if we're given x's and we want to find their y's. We actually have to plug them into the function for sine x. And we've actually done stuff like this before in our first unit, but we haven't written them as like x, y coordinates. So I want you to take your calculator. We're going to enter in sine of 0 and press equals, and you'll notice that you're getting out 0. Then I want you to do sine 30. You should get half, or 0.5. Okay, if you want, you can use exact values here, but you may need to know what these actually are in terms of decimals in order to graph this in a second. Okay, and then we're going to do sine 60, which we know from our special triangles is root 3 over 2, or approximately 0.87. Okay, so you're going to do that all the way down for this table of values. And then what you're going to do after you're done that is you're actually going to go and graph these as xy coordinates. So I'll show you what I mean here. So we're going to graph the coordinate 0, 0, which is of course the origin. And then we're going to graph the coordinate 30, 1/2. That's here. And then remember, this is 0.75. And then we're going to go 60, 8.75. It's going to be something like this. Okay, and then you're going to keep going, graph each of your points, and then you're going to connect them all once you're done. Okay, so pause the video. You're going to take a second to do this, and then we're going to discuss this information here. Okay, so this is what you should have got for all your x and y coordinates here. And when you graph, it should look something like this. So when you connect these guys, you're going to connect them with a nice curved line here, like so. Oops. And this is what we should get. Now this graph actually does extend in both directions, so we're just going to put little arrows on the ends of this as well. And we'll label this f at x equals sine x. Okay, so a little bit of information about this. Sine x is a periodic function. We don't see all of it. This is just one cycle of the function. For your homework, you're actually going to extend this back. So you're gonna go from 0 to negative 360. So you can actually add on to your table of values if you want, or you can kind of just extend the pattern in a backwards direction there. This is always actually continually repeating toward the left and toward the right. So that makes the domain of this function all real numbers. So we're going to say x is an element of real numbers. And what this also means is that I can plug in anything for x here that I want. Any number, any negative, a positive, I can plug in a decimal. I can plug in 1,000 if I want, and I'm going to get a value out for x. There's no restrictions on x. However, you will notice here that if this continually repeats, there is a maximum and a minimum here. And that maximum is 1, and the minimum is -1. So what we want to say for our range here is that y comes from the set of all real numbers, but it needs to stay between 1 and -1, and it can also equal those because we actually see those on our table of values here. Okay, so as I said, if this is showing us one cycle, that means that one cycle must take from 0 all the way to 360, and then you'll notice that the pattern continues after that. So the period of the sine function is 360 degrees. Okay, now if we think back to our quadrants from last chapter, why would, well, you don't have to write cast, but why does it make sense that one cycle would take 360 degrees and then it would start repeating again? Well, if you imagine your arm kind of moving around this circle, it only has so many unique positions before it starts repeating again at this point. and then it's going to repeat those again and again and again, right? So once we've done one full rotation around, the next rotation around that cast grid is going to give me out repeating values from before. So that's the idea. That's why it's 360. Okay, and then amplitude. So amplitude, remember, we can calculate by doing max minus min over 2. And we just said that the maximum was 1 and the minimum was -1. So if we calculate here, we'll basically just end up getting 2 over 2, which equals 1. So this is probably more applicable to the stuff that we're talking about with like amplitudes and waves. We're looking for the resting point to the max, which is 1 unit, and the resting point to the min, which is also 1 unit. So that's our amplitude. Okay, now we're going to do the same thing for cosx. Okay, so same table of values, except this time we're plugging into our calculator in for cosine, and same setup with our graph. So I'm going to give you a couple minutes. You're going to type the cos of each one of these angles and record the values here, and then graph the corresponding points below. Okay, so pause the video and take some time to do that. So this is what you should have got for your y column here, and then you should have graphed points that kind of make this formation down here. Okay, and you're going to connect those points just as we did the last time with a nice smooth curve. And you'll notice a couple things here. I'm adding some arrows, but I'm making sure that my graph kind of like it turns down after that and it doesn't go like up into the air, because these top points here are actually maximums. So it will curve downward from there. This is also a periodic function. This pattern will continue repeating again and again and again as we continue extending in both directions. So what's visible here from 0 to 360 is just one cycle of this periodic function. Okay, so domain and range for sine and cosine are actually very similar. The domain is all real numbers. Okay, it can be anything. It continues in both directions forever. And the range has a maximum and minimum value. So you can see here that the maximum is 1 and the minimum is -1. So same range as sine. Y must be equal to -1, but greater than -1 and less than or equal to 1. Okay, the period also is 360 degrees. And the amplitude will be 1 as well. Okay, remember this is a displacement from the resting position to the maximum and the resting position to the minimum. So that's 1 unit. Okay, for your homework as well, you're going to extend this guy back in this direction all the way to -360. Okay, and lastly, we just want to take a look here at transformations of sine and cosine. So we're translating some of the information that we learned in our transformations unit into transformations of sine and cosine. So I want to remind you about what the a, k, d, and c values do. And also, the a, k, c, and d values do tell us something about the graph features of these periodic wave functions, like amplitude, period, and things like that. Okay, so from our transformations unit, there is information that we can get about like vertical and horizontal stretches, compressions, and shifts. So if a is greater than 1 or less than -1, you have a vertical stretch. If a is between 0 and 1 or -1 and 0, you have a vertical compression. And if a is negative, or in other words, less than 0, this is a vertical reflection. A also tells us information about the amplitude of the periodic function. So if we take the absolute value of a, and just to remind you, if you're not completely sure what absolute value is, the job of the absolute value function is to make any value that's put into it positive. So positive values that are put in remain positive, but negative values that are put in are made positive by the absolute value function. So the absolute value of A will actually equal the amplitude of your periodic wave function. Okay, similarly for K, we can get horizontal stretches, compressions, and flips. So if K is greater than 1 or less than -1, this is actually the reverse of A. It's going to be the horizontal compression. Whereas if K is between 0 and 1 or -1 and 0, this is going to be a horizontal stretch. And if K is negative, or in other words, less than 0, this is a horizontal reflection. K can also tell us some information about the period of the function. So if I take a look at the K value, if I take my K value and divide it into 360, it will actually give me the period of the function. And if I rearrange this, if I happen to have the period, I can also find the K value of the function. So if I multiply K up and divide out the period, K will also be equal to 360 over the period of the function. Now, typically, K in these cases will never be positive, will never be negative. But if you happen to see something that's negative in your travels, we do want to make sure that the period is a positive value, as I mentioned above. So make sure you take the absolute value of K if it happens to be negative. Okay, and then C and D, these are translations. So C can shift our graph up and down, as we know. A positive will shift our graph up, where a negative will shift our graph down. We often call this, when we're referring to these periodic functions, we call this vertical displacement rather than vertical shift. Okay, and then D also has a special fancy name when we're working with periodic functions. We call it phase shift. Okay, and if D is positive or negative, that will shift our graph left and right. But remember, with the D value, it looks opposite of what it is in the equation. So this still holds true because of this negative that we see in here. So if D is positive, it will actually look negative in the equation, and vice versa. Okay, we also want to just take note and make sure that the K value is common factored out from the X and D, or we won't see the proper D value shift. So always make sure that K is common factored. Okay, so let's take a look at some of this information here as far as graph features and see if we can pick this out from a few examples here. Okay, so we want to fill in the following information for this graph here. Oftentimes we will use theta in here just to represent like the actual angle. It's no different than the X that we just used in our investigation. So if you feel more comfortable letting that be X, that's totally fine as well. It's just a variable is what it is. Okay, amplitude. So absolute value of the A, which is 3 here. And that means that our amplitude is 3. Period. We can find this by doing 360 over the absolute value of K. And this will simply be 360 over 2. So our period here is going to be 180. Phase shift, this is essentially going to be taken from the D value. You're going to specify right or left. So this one, we'll see that D is negative 60 degrees. So we'll say 60 degrees left. Okay, vertical shift, or sometimes you'll see vertical displacement here. That comes from our C value. So because C is -1, we're going to say 1 unit down. Okay, and then this is asking us about max and min. So the interesting thing, and we're actually going to add this onto C as well, is that C is actually what we call the resting position or the midline of our graph. So let's just add that. This is the midline of the graph. And what this means is that the amplitude is actually measured from this resting position. So if I have my wave function will kind of go up and down equal distances from that line. So I'll actually measure the amplitude from that center line to the maximum and from the center line to the minimum. And that center line will be C. So if I know the C value and I know the amplitude, I should be able to count up the amplitude from that C value and down the amplitude from that C value to find my max and min. So here's what I know. I know that my C value is -1. And I know that if I count up the amplitude from that, which is 3 units, I should hit the maximum point. So what's 3 units up from -1? Should be 2, right? So our maximum should be 2 here. And then if I use the same kind of idea, if I know my C value or my midline is 1, and I count down the amplitude from that, which is 3 units, I should hit the minimum value. So what's 3 units down from -1? This should be -4. Okay, so as kind of a summary here, we can basically say that the maximum can be calculated by doing C plus the amplitude, and the minimum can be calculated by doing C minus the amplitude. Okay, I personally just prefer to kind of think about it logically in terms of counting up from the midline and down from the midline. But if you want to memorize these formulas or have those on hand, you can definitely do that. Okay, try this one yourself, see if you can fill out the information, pause the video, and then we'll come back and take it up together. Okay, so now that you've had a chance to try this on your own, amplitude, you should have done the absolute value of -2, which should give you +2 for this one. Make sure that you take the absolute value. Amplitude cannot be negative. Now in this one, if we don't see a K value, you're going to assume that your K value in here is 1 when we don't see it. So in order to calculate the period here, there's no stretch or compression that has happened. So the K value should remain, or the period should remain as 360, what the normal cosine period is. Okay, phase shift, we have a D value here of 30, which means that we're saying our phase shift is 30 to the right. Vertical shift or vertical displacement, this is going to come from our C value of 5. This means vertical displacement is 5 units up. I guess we'll say units. Okay, and then max and min. So if my C value is at 5 and I count up my amplitude from that, which is 2 units, I should hit my maximum. So up 2 units from 5, that should have given you 7. And then similarly, if my C value is 5 and I count down the amplitude from that, I should hit my minimum. So 5 minus 2 basically is the calculation we're doing here. Should have given you a minimum of 3. Now guys, use your common sense. If you get a minimum that's larger than your maximum, that does not make sense, and vice versa, right? If my maximum is smaller than my minimum, I must have done something wrong in my calculation. The maximum needs to be a bigger value than your minimum. That just makes sense in terms of our common sense. So use your common sense here. Make sure your max is bigger than your min.